Good morning, good afternoon, good evening, everyone. Welcome to the first event of the INSEAD AI Global Leader Series, organized by Digital at INSEAD, INSEAD Lifelong Learning, the INSEAD AGI Student Club, and the INSEAD AI Alumni Club. I'm Eugene, professor at INSEAD since 2001, after having spent 10 years in MIT, where I did my undergraduate and my PhD in AI. We have today with us two really exceptional guests that I will introduce shortly. Next slide, please. The INSEAD Global AI Leader Series features an amazing lineup of people at the forefront of AI today, covering research, business, and policy, and bringing perspectives on this very important topic from all around the world, including China, Europe, Israel, Singapore, UAE, and US. Don't forget to register for each event separately. We'll soon send again a link in the chat shortly. Next slide, please. Just briefly, the webinar etiquette as usual. The audience is muted with video off. The chat is on, and we will be putting some notes there. The webinar will be recorded, and for any technical issues, please email digital@insead.edu. Next slide, please. It's an incredible pleasure, and personal pleasure also, and honor, to have with us today Amnon, Shashua, and Poggio, arguably two of the most important people in the history of AI, and you will see why shortly. Next. Amnon Shashua is a Sachs professor of computer science at the Hebrew University in Jerusalem and an incredible serial entrepreneur. He's founder, president, and CEO of Mobileye, a public company at NASDAQ with a valuation of 25 billion in the space of autonomous driving. He's co-founder of Orcam, a unicorn AI company for the visually impaired, co-founder and chair of Israel's global unicorn player in the LLMs and Gen AI space, AI21 Labs, making machines thought partners to humans, founder and owner of a bank, and co-founder and chair of a new humanoid company, Mentee Robotics, that he unveiled yesterday. He's also a founder of two more companies which are currently at stealth mode. Amnon received his PhD in MIT in 1993. Of course, with such a guest today, you may be asking, who is the other guy, Tommy? Next slide, please. Tommy is a key protagonist in the history of AI. He has been working on the science and engineering of intelligence for more than 50 years. He did his PhD in Italy at the University of Genoa in 1971. Then, after spending a few years in Germany at the Max Planck Institute for Biological Cybernetics, he moved to MIT at the AI Lab just a few years after the lab was created, where he has been a professor for the past 43 years. He has been a director of multiple labs in MIT, including CBCL, the Center for Biological and Computational Learning, CBMM, the Center for Brains, Minds, and Machines, which has been at the roots of today's MIT Quest for Intelligence initiative, where Tommy is also a member of the leadership team. He has been an advisor of many PhDs and postdocs, including the postdoc advisor of Amnon and other such impressive AI people, including a postdoc advisor of Demis Hassabis, the founder and CEO of DeepMind. His life is not only a history of AI, but also, in my view, a beautiful history of a scientist and of modern science. Reading his autobiography, and we will share a link to it in the chat in a minute, is literally like going through a journey with amazing people, including more than 30 Nobel laureates he has been interacting, working, and going on vacations with, such as Francis Crick, Richard Feynman, Paul Samuelson, and many others. Tommy is joining us today from Tübingen, while I happen to be instead just down the corridor from his office in MIT as we speak. We just miss each other this time, but we meet often. Tommy is in Tübingen giving a keynote in an event for the 100 years since the birth of his early collaborator and friend, Werner Reichard, a German physicist and biologist who helped to establish the field of biological cybernetics and co-founded the Max Planck Institute for Biological Cybernetics. Next slide, please. Let me end by saying that this is a very special event for me personally today. I got to know Tommy and Amnon almost 30 years ago for my master thesis and then PhD in machine learning in MIT. With Tommy and Amnon, I wrote my very first article in 1997 on what one calls today deep fakes, as you see here. It has been an amazing luck honor and pleasure to know Amnon and Tommy and to be mentored by them. Amnon, you may not remember this, but you gave me one of the most memorable advices in my career, while Tommy has been an incredible advisor, mentor, inspiration, and dear friend for me for many years. Amnon, Tommy, welcome. So I hope I see you are there. Yes, Amnon is there. Tommy is there. Thank you very much for making the time. It's a real pleasure and honor to have you here. And I'm sure all the audience and the INSEAD alumni and beyond will benefit from this. Let me start with two questions for you both. You've been working on this for decades. And as I mentioned, we worked on this almost 30 years ago. First question, and maybe two questions together. Is the kind of AI we have today what we imagined 30 years ago? In one sense, yes, and in what sense, no? And also, if you could share with us, what have been the 2 or 3 most significant and maybe surprising ideas and discoveries that took us where we are in AI today? Amnon, welcome, if you don't mind starting from these questions, and then I'll pass to Tom.
Okay. Thank you, Theo, for the very kind introduction. Well, AI that we thought 30 years ago, I'll actually paraphrase Tommy. These are things that we discussed actually 30 years ago. So the kind of image that we had 30 years ago is, imagine, a spaceship coming from an alien culture 1 million years ahead of us, landing on Earth, and they're altruistic. So they didn't come to conquer us or do any harm. So what should we do with them? So we'll ask them questions about problems we don't know how to solve, about sustainability, about energy, about medicine, right? Because they're 1 million years more advanced than us. This is the kind of AI that we thought 30 years ago that someday would emerge. The AI that we have today, is very impressive. I can say a few words about that later. Is very impressive, but this is not the AI that we thought 30 years ago. The AI that we have today, is converging towards, becoming a good assistant. So someone with a, high school education, maybe bachelor degree education, you task this, assistant to read for you a number of articles, summarize for you, do a sophisticated internet search, create PowerPoints, create Excel files, maybe write code on not too complicated things, but write code for you. So what a good and educated assistant can do. It's not, a great scientist, it's not a great mathematician, not a great physicist. No. So that part is still missing. And really the question that we scientists and practitioners ask ourselves is this gap between, having a good assistant to having a great scientist. This gap requires another scientific revolution, or this is just an incremental progress that we need to make, given the AI that we have today, some incremental progress, and we'll get to the AI that we imagined 30 years ago.
Yes, I think I agree with what Amnon said. I probably not 30 years ago, but 20 years ago, I was probably dreaming of having something like Alexa was probably just there, something that could work in the car while driving. I could chat and ask for looking at papers on the web and have a summary of them. And I must say that this is what we have today. ChatGPT-4 or Gemini ChatGPT in particular is very good at understanding my speech while driving, and very kind in telling me information about some mathematics I'm curious about, not much depth in explaining, but a nice person that when I arrive home, I ask me, do you want more details? I said, no, we should stop here because I just parking the car. And he said, I'm happy you arrived, and let's speak more about it tomorrow and have a good night. And all of that it's very nice. And, it's kind of almost beyond what I expected, but but it's not beyond those kind of dreams. It's not what Amnon was describing as the civilization that is super intelligent, that can give us answer to the mysteries of science and life. Not yet.
Tommy and Amnon, maybe both of you, what do you think have been the 2 or 3 we can share, in your views, big breakthroughs, or maybe surprising findings, theories, ideas throughout the history of AI, and maybe also recently, that took us here? What would be like your top in your mind? Maybe
Well, I'm surprised by the progress we have made on intelligence, or the field has made on intelligence with big data. I was expecting perhaps a big idea to have to be a breakthrough in this quest for intelligence, in understanding what is arguably the biggest problem in science that we have, the nature of intelligence. Instead is big data. So that's one surprise. Another one is, I think the power of deep learning has been very impressive, also in success stories like AlphaGo, that are mainly using another important advancement in machine learning, which is reinforcement learning. And the third one, recent, that surprises me is the unreasonable effectiveness of predicting the next word. It seems that we can capture a lot of, at least superficially, a lot of human intelligence by training a system to predict the next word. It makes sense, but the effectiveness of that is it's surprising. It may be also misleading. Maybe that's not the way to real intelligence, and that's the topic maybe we could discuss about, whether large language models today will be able to give us systems that are really intelligent, or whether we need a completely different approach.
Let me go back to what Amnon said about AI being a scientist, maybe AI being able to abstract. Today, people talk about whether AI can even reason. And in one talk, I remember, Amnon, you mentioned actually that's not the necessarily difficult problem. The difficult problem is abstraction. What would you guess, if you can guess, we would need, of course, it's hard to tell, to get there? And what does it mean? And what can we do if we manage to create AI which can reason? Can we do this? Are we almost there? And B, understand abstraction? And then what can we build? What does it mean? What can we build with this?
Yeah.
Amnon.
Yeah, well, in order to understand where we want to go, we first need to figure out where we are right now. Now, it's a bit tricky because those big AI language models are developed by companies. And the companies, even if they call themselves open, they are very, very closed in terms of, they keep the cards very, very close to their chest in terms of the limitations of the systems, what they're exactly doing. So we as scientists, we need to kind of explore and try to understand what are the real limitations of these systems today. And there are some telling signs. I'll give you one telling sign, which I think is profound. A couple of months ago, there was kind of a test being conducted on having all the language models, both proprietary and open source, try to solve a Hungarian math test. It's a high school test, not very difficult test, but still it's a high school level, matriculation test in mathematics. And the language model that succeeded the best by really a large margin compared to all the other large language models was GPT-4. That's not surprising. And then what was the score that GPT-4 received? It received a score of 68 out of 100. which is impressive. That means 5 years ago, if you had asked me, do you see a machine learning algorithm solving a high school level matriculation exam at the, with a score of 68, I would say, I don't know how to do that. It's science fiction, right? So it's impressive. But then you start scratching your head and you ask yourself, what kind of student gets 68 in a math exam? So the kind of student that does that is a student which overfits, meaning the student solves a lot of problems and hopes that in the exam, he will receive a problem that is similar to the problems that he solved during practice. So in statistics, we call this overfitting. A student that receives 100 in an exam goes one level up. The student kind of figures out the rules, the abstractions of the material being learned. And then with these abstractions and the rules, he can go and solve any problem, even problems that are not similar to the practice problems, in the homework problems, right? So we can, and there are many more signs like this. So we can say that, the existing AI today, like GPT-4 of AI, is based on massive overfitting. Okay, now this is not necessarily bad, right? So 10 years ago, machine learning of 10 years ago would say that overfitting is bad. But today, when we look at the success of these language models, maybe overfitting is not that bad. The question is whether we continuing to overfit, can we make this jump from a system that can solve problems through overfitting to a system that can solve problems after understanding the rules behind the data and performing the right abstractions and then solving problems, right? This is the gap that we have today. And then going back to what Tommy mentioned, do we need to kind of have another scientific revolution, a new architecture of learning in order to make this jump, or simply continue with the same path that we are on today, more data, better data, and make this jump? So 6 months ago, I would say that no, we need some revolution. This gap is too big. Today, I'm not that certain. I think there are more signs that show that making this jump is not really far away from today. Okay, but we can continue talking about this. I don't want to make now too long of a lecture. We can continue talking about it, but I think this is the point. These systems have the semblance of reasoning, not too sophisticated reasoning, not too deep reasoning, because it's really based on massive overfitting. And our challenge, if we want to go to the next level of AI, is how do we make these systems, discover rules? How do we make these systems abstract in order to solve a matriculation exam at the score of 100 and not the score of 68?
So there is something amazingly potentially profound here. First of all, to begin with, this relates to overfitting and big data that Tommy said. It seems like this big data that captures human language, which is a representation of human thought in some ways, is enough for training an AI that can reason and generate language that sounds like human.
Yeah.
So the question you're raising is whether big data is enough to also get to abstraction and higher level of thinking, if I may use that.
That's
which
right.
would mean, if that's the case, it would mean that somewhere in the data that has our mathematical solutions, proofs, arguments, books, writings, you name it, that data also has somehow captured our abstract thinking. But it could be that language does not capture our abstract thinking at all. And I'm wondering, Tommy, where you stand on this. Amnon seems to be optimistic relative to 6 months ago that just with big data we can reach maybe everything that humans can do. Do you think so, or do you think there is potentially something else?
No, I think it's possible, but it's not completely clear. Think about how our intelligence arose, how evolution invented it. It probably the evolution of intelligence started with primitive associative reflexes, basic sensory input and motor outputs, associations. These are essentially associative memories. I think this is likely to have been at the beginning of the discovery by evolution of eventually human intelligence. But then at some point, our brain, our mind became able to produce theories, abstraction that make sense of a bunch of facts. What Cicero, the Latin writer, called induction, from the Latin inductio. So evolution arrived probably through language, but it may have developed an architecture that is different from transformers, maybe in some important details, or maybe in a quite different way. So that's a big question, whether we need something different for transformer, or we need to add something to transformers. And one way, there is no way, I think, to know. The only way is to try, and there are many scientists and many companies trying to do that, especially in trying to improve transformers and what they do. And I'm sure A21 Lab is one of them.
So just for the audience, transformers is basically the deep learning architecture. Think about neurons and artificial in this case, or units that do some calculations connected with each other in a specific architecture. But Tommy, I'll jump a bit ahead of on this topic of transformers. Is transformers the way it's structured today? Is the architecture of today's AI, let's say, brain, having any similarities to things we know exist in our mind? And are there any major differences that actually are not captured in today's architecture that could give some indication about what could be the next breakthrough beyond transformers that was developed, as we know, from Google and was used for GPT-4 and everything else today, more or less? What are some views on this, on the architecture of the brain versus the AI?
Yes, well, a transformer is made up of two basic parts, so to speak. A transformer block is part of it is what is called multi-layer perceptron. So these are artificial neurons heavily connected together, densely connected. And then there is a part called self-attention, which does a selection process of the kind of tokens or words that are important for predicting the next word. Now, the MLP part, the multi-layer perceptron part, that is, what actually came into this architecture as inspired from the brain. So that's consistent what we know about the brain. The attention part is not. It could be, but there is no obvious part of the brain or cortex that does that, although there are possibilities. Difficult to say whether it's consistent or not with the brain. It could be, but there is no obvious proposal of where in the brain something like that could happen.
So two key takeaways here. Sorry, maybe interrupted. Two key takeaways here: big data and memorizing / overfitting with vast amounts of data, using an architecture today, transformer, and a couple of others for images and videos potentially, which are not necessarily similar to the architecture of the human brain, at least. There are probably other animals also. And potentially the innovations in the architecture of deep learning can take us to the next step, combined with big data, to create new capabilities beyond memorization and beyond prediction of the next word, with better reasoning and potentially abstraction, making AI potentially the best scientist history ever saw. And I'll come back to this later. Amnon, you are into also autonomous driving, among 1,000 other things you are doing. And there we are more or less somewhere between L2 maybe and L3, level 2, level 3 autonomous driving, not level 4, fully autonomy. And in a sense, from our discussions, I understand from what you say, you consider GPT-4 and today's large language model and AI being more like a level 2 autonomous driving, where you need assistance basically from a human. Can we go from level 2 to level 4 quickly? And what do we need to get there? Let's start first from the autonomous driving, and then more generally in AI.
Well, in autonomous driving, I think it has been proven that you can do level 4. This is, Waymo. You go to San Francisco or to other cities that they are operating, you order a Waymo taxi, comes without a driver and takes you quite safely, as far as I understand, from point to point. So I think that the technology is there. The ability to drive autonomously is there. The question is how to scale, how to bring these systems in mass volume. So it's a matter of also cost, how to build a business around them. And this is what we're doing at Mobileye. We see that autonomy is basically 3 different stories. The public is aware only of one story, but there are 3 stories around them. The first story is that if you have a vehicle that is equipped with multi-sensors, multi-cameras, cameras surrounding 360 around the vehicle with other sensors like radars and lidars, you can provide a much higher levels of safety. That means the car can avoid accidents, not only longitudinal accident, but also lateral accident. If someone is approaching you laterally, your car will offset, your car will do evasive maneuvers to avoid accidents. So this is a safety story. So just, having computer vision and AI processing full surround sensing can enable safety levels that are much higher than safety levels today. So this is one story. The second story, if you can provide a level 3, so it means that on certain roads like highways, you can work on your smartphone and not pay attention to driving, and the car will drive safely along those road types. The value proposition here is buying back time. We sit a long time in the car. 90% of our time are on primary roads and highways. If we can do something else while driving those stretches of road, that's a big value proposition. So this value is, let's call it buying back time. The third value proposition, which is related to robotaxis, this is having a much higher utilization of vehicles that are involved in mobility. And the story here goes that in a taxi, if you remove the driver, you are removing 85% of the economical cost of a cost per mile. And if you replace this with CapEx, it means with a robotic driver, with a computer, then you can quickly have a return on investment on the CapEx and then have a cost per mile, which is much lower than the cost per mile today. And therefore, it will incentivize large cities to be mostly driven by robotaxis than by personal-driven cars. This is one part of the story. The second part of the story is that there's a shortage of labor. And this shortage of labor can become worse over time, that you'll not have enough people that are willing to drive trucks, drive taxis and shuttles and so forth. And if you can have this done by by computers, then you'll be solving a big problem, which is a labor shortage. So those are 3 stories, and the 3 stories can be pursued simultaneously. And this is what Mobileye is doing. We have systems that have full surround sensing. Today in China, about 200,000 vehicles with these systems, and they're coming to the West this year. And you still need to supervise the driving. But in 2026, we announced that with Audi and with Porsche, you'll have a system that you don't need to supervise the driving. So on highways, you can simply let go and work on your smartphone or read a book, and on highways it will drive autonomously. And we're also working with partners like the Volkswagen ID Buzz, which is a vehicle platform that in 2026 will have also robotaxis, few tens of thousands of robotaxis. So I think autonomous vehicles is not a scientific technological problem anymore. It's more how to productize it and build it at scale, reach the cost levels that will enable building it at scale. Now, if we go back to GPT-4, you know, the kind of vision that people have with GPT-4, they call this agents. So imagine that you have a Slack group, and one of the members of the group is an AI agent. And in the group, we give tasks to each other, and we give also tasks to the AI agent. Read an article, summarize for us, create a PowerPoint describing this and that idea, and so forth. Now, nobody wants an idiot in the Slack group, right? So the tolerance for mistakes is very, very small. So even if this agent 80% of the time, you know, performs correctly, you'll be judged on the 20% of the time that you don't perform correctly. So this is like level 4. On the other hand, the use that we have today with the kind of large language model is like level 2. We are very tolerant to mistakes. We ask it a question. You know, if it answers correctly, we're happy. If it doesn't answer correctly, then it's okay. Then we do our Google search and find the answer ourselves, right? So this jump from level 2 to level 4 in the GPT-4 world is also going to be a challenge, because the tolerance for mistakes in an assistant that we rely on is going to be very, very small. And understanding where are those areas that the agent does not make a mistake is going to be a big challenge, because these agents, you know, this AI today suffers from hallucination, suffers from not being factual, and making it factual, 100% factual and 100% correct, even in a narrow set of problems, is still a challenge.
I'll come back to this in a second, but now you are making me think about when is it time to start building a product/business around these technologies. And I was always impressed and surprised by your choice, your decision, a long time ago, more than 25 years ago, I think, that you started Mobileye. How do we know it's time to build a product? How did you find out? How did you decide to do this? A long time before everybody was talking about autonomous driving in some ways. And how does one manage technology risks? If you can share something also in general from your business experience or lessons you learned from your business experience about managing technology uncertainty risks. What would be some lessons for the audience?
Well, you know, I'm not a typical entrepreneur, because first and foremost, I'm a scientist. So I'll never open a company that solves a simple problem. It's only if it's a deep problem, right? Only if it's something that is very, very difficult to solve. Otherwise, because you know, not every company solves difficult problems. There are companies that solve simple problems and they make a lot of money, right? You know, building a social network doesn't require deep technology; it just requires luck that your particular social network succeeded, right? You know, who would predict that TikTok would succeed as much as it succeeded? It's not because of some deep technology. But I'm interested in solving deep technology. So Mobileye is really from day one was trying to solve problems that others thought that's not possible to solve. For example, having computer vision 25 years ago be productized to a point in which it can, you know, avoid accidents in a very low-cost manner with a single camera. Today, it sounds obvious. 25 years ago, it was really science fiction. Robotics, I think it will take time until we'll see robots, you know, performing tasks like humans. But I think the technology or the science is there. I mean, it could take quite a long time until these robots will be produced at scale. But the science is there. And when the science is there and you are solving a real problem, because there is shortage of people in many mundane tasks. example, in warehouses, in production plants, even in domestic chores. There's a real shortage of people who are willing to do mundane chores, and if this can be relegated to robotic beings, then this solves a big problem. So the science is there. This is why I decided 2 years ago to start a robotic company. Language models. Language model is tricky because how exactly to make money from language models is still an open problem. It's really a bloodbath going on there, right? There are so many companies producing language models, some of them open source, some of them not open source. You pay a subscription of $20, whether this is a monthly subscription, whether this is sustainable, not sustainable. It's still an open question how to make money from language models. But I think AI is so profoundly going to change society that it's worth the risk to start building the technology and later finding the right business model for that technology, because this kind of technology is so impactful on society. It is worth plunging into it, even though exactly where the money is going to come from is not that clear. Is not that clear.
So it sounds like it's important to have a sense of where science is today before starting something new. And when science is there, and this requires quite a bit of experience that you two, of course, have exceptional amounts of, then one can manage the rest relatively easier. The big question is the science there? Which takes back to what we said before about abstraction and other things AI can do. Let me switch a bit gears and move a bit to behaviors, people, personalities, humans, and AI. And Tommy, I'll start with you with a non-AI question, and then come back to you, Amnon, with an AI version of that. So, in your autobiography that we shared on the chat, you have worked and interacted with all sorts of amazing people that most of us read in the books about, like Richard Feynman, as I mentioned, Francis Crick, and a couple of dozen other Nobel laureates. So a question for you before we go to AI, it's personality. And that's what has to do with the personalities of AI. What personality traits you find most impressive among the many people you interacted with in your life? And then let's see whether we can actually engineer those personality traits.
I met a number of very interesting and smart people, of course, different from each other. That's part of why they were interesting. But the kind of things I liked most was, of course, the love for science, having fun in doing science, the focus on it, but especially the enjoyment of doing it. And that has been, for instance, of one of the people I've met, who is definitely one of the most impressive ones, is Francis Crick, and he was really like a child having a lot of fun thinking about science and working on it with other people. And it's not, I think it's not strange that he looked for young people to do that. It was essentially a way to keep alive and happy.
It's beautiful, Tommy. A way to keep alive and happy is basically curiosity for understanding, which is science.
Yeah.
And the next question, of course, is: will we make AI have curiosity, which means it's to begin with, or in general? Amnon, I'll go back to you because you have announced a number of exciting things about how to build. Let's go back to cars for now, which is robots basically in a sense, right? It's a good test bed for AI in general. And cars can have, much like their drivers today, different kinds of behaviors, attitudes, personalities. Some are aggressive, some are polite. Polite in a German way versus an Italian or a Greek way, very different politeness, or maybe Israeli way, very different. But you have announced an approach to building what you call like different driving experiences, a platform for driving policies that can enable different car makers tuning AI to create different driving experiences, meaning different personalities. Can you tell us a bit more about this? How is it structured from an engineering point of view and product point of view, and what it means going forward for AI with behaviors?
So no, we were kind of struggling with thinking about how to make sure that we build these sophisticated systems at scale. Now, one thing that could prohibit scale is customization. Let's assume you build a system and each car manufacturer wants to customize it to a point in which you really need to do everything from scratch. Now, where this customization comes from, there is a kind of an axis where between something that is universal and something that is, I would say, specific. Universal is computer vision. If you have a system that needs to perceive the world, you don't need to really customize it. It's universal, right? There's no reason why an Audi vehicle would interpret the world different from a BMW vehicle or from a Hyundai vehicle. So you can build a perception system which is good enough to understand the world to an actionable level, for example, for controlling a car, to avoid accidents or to do hands-off. And you don't need to do much customization because it's universal. Where it becomes complicated is when you're starting to make decisions, starting to control the car, say in a hands-off situation, making a decision. It's not only the braking profile. Say, for example, you want to change lane. You can be aggressive, you can be less aggressive, assertive, to whom to give way, whom to take away in a driving scenario. Each car maker, each customer will come with their own requirements. And it could be a real nightmare because at the end of the day, you need to validate these systems. And car makers, they claim rightfully that this is something that they need to control because this is the look and feel of the driving experience, right? So then we came up with a way to split. It's called driving policy, the making decision, to split it into a universal part, which contains all the AI heavy lifting like path planning and optimizations, but the more specific parts like describing the braking profile and the tactics of whom to take way, whom to give way, and then this split allows the car maker to write their own code on top of the universal part of driving policy without us thinking about how to customize. And in that way, we can build a system that you don't need much to customize because the customer, which is the car maker, can write code on top of that system and writing only the specific parts of the driving policy and not the universal part, which are really AI enabled, very, very heavy use of AI. And finding this dividing line was kind of very, very tricky until we found it in a way that enables the car maker to write simple code to do only the specific parts that control the driving experience, where we do the AI part, which is basically kind of an operating system of driving policy. So in that way, we solve the scalability problem, because otherwise you cannot scale. If every car maker wants to control the driving experience, and driving policy is something that you need to validate, and you need to validate over millions of hours of driving to make sure that you're not making a mistake, or that it becomes impossible to scale. So this is something that we announced half a year ago, and was a great success with car makers.
So an example of a driving policy, just for us to understand, what are examples of driving policy? BMW.
So the driving policy is kind of decisions how you merge into traffic. So you're driving, there is a route that you want to follow, and you need to kind of exit your highway or make a turn, whether it's protected turn or unprotected turn, in order to follow your route. And then you need to negotiate with other road users, whether these are pedestrians or other cars. For example, you want to change lane and the traffic is congested. You are signaling with your turn signal, nothing happens. So because they don't give you way, so you start pushing, and you are signaling to the other cars that you want to change lane. Some of them will allow you to change lanes, some of them will not. So you have to make a decision, whom I'm going to take way, whom I'm going to give way. So there's a lot of negotiation going on in merging into traffic. This is why we take driving lessons. It's not something that is natural for humans, right?
So basically, when you say you in this case, is the AI driving the
It's
car?
the AI, exactly. So a human, a 16-year-old child goes and takes driving lessons because it's not a simple problem. It doesn't come natural.
So basically, the AI is negotiating with other AIs, other cars, and with humans, pedestrians,
Exactly.
on how to collectively behave, which sounds like it's amazing we can actually build this today. It's kind of negotiation with different kinds of politeness measures or experiences in general. It's fascinating we can do this, and it's another miracle in some ways, one can argue. I have some questions about going forward, but I'd like to take a quick pause for yes/no questions with a quick answer first. Just go there and then go to the future, if you don't mind. I think a couple of them we answered already, but let me go through them anyway. For both of you, yes, no, and maybe a quick answer why. Do our brains have any architectural components that look like those used in AI today, like transformers? I think we answered this, or maybe I skip it because from what I understand, Tommy, you said
No.
not clearly.
Not clearly, yeah.
Clearly. So the next question then follow-up is, does this mean potentially that transformers, which are behind today's AI and today's leading models, will soon become old technology? And when I say soon, next 1 to 3 years. Do you think that will be the case, that there will be a disruption of today's AI leaders by new architectures? Yes, no?
I think yes, but probably not in 3 years.
Amnon?
I think no. I think the game is going to be a data game rather than an architecture game. I can elaborate later.
Okay, data versus architecture. So one of you sorts OpenAI, the other of you doesn't sort OpenAI, kind of, in a sense, right? So let's see. We'll find out. Next question. Will we have another AI winner as we did before? Why or why not? What's different today?
No.
Amnon?
Yeah, I agree with Tommy. I don't see an AI winter. There's a great success already.
And what's different from the previous? Why did we have AI winners before and not now?
It was not successful.
Yeah. Now it's AI makes money, a lot of money, even at the stage in which it is, which is not the final one, but it makes already a lot of money. There are a lot of applications, useful applications. So, yeah, I don't think.
Okay. Next question. Going back to the scientist AI, which eventually, if the AI is a scientist, it can solve all sorts of problems, right? So will the next 50 years, I put a random number here, of course, AI become a scientist better than any scientist in human history? Yes, no?
I believe yes, and in the next less than 5 years.
5 years?
Yes.
Wow, Tommy?
Eventually, yes, but not in the next 5 years.
Okay. Obviously, there is variance, but at least both of you say yes, which I'm curious what this means practically. And maybe we'll come to this after we go through the yes/no questions. What does it mean practically? What does it mean that AI becomes a scientist? What will change? What kind of new products can we have, or what kind of new solutions? Let's come to this in a second. How about a poet? Will be better than, how about AI becoming a better poet than any poet in human history? Yes, no? Already is?
I think yes.
Yes, yes.
I think this is already happening. I mean,
Exactly.
I'm very impressed by things that, the large language models can write.
Okay, so you both agree on this. Last yes/no question. We'll go back to longer discussion. What will eventually be more intelligent? A, cyborg humans with implants, like Neuralink kind of thing, enhanced with AI, or B, AI alone, in which case, if B is the answer, this will probably prove that human chemistry and human nature are actually limitations to intelligence. What do you think, A or B? Tommy, cyborgs or just AI alone?
More intelligent is intelligence it's a funny story. It's not one-dimensional. You have different forms of aspects of intelligence, and so I'm not sure.
For some instance, maybe.
Sorry?
For some.
We may have to go anyway through cyborgs in terms of what will happen. And
oh, sorry.
No, I was saying this is, by the way, one reason why one of the reason why we should at some point try to understand how our human intelligence works, how the human brain works. We need to know where to put the plugs and what are the protocols for communicating, between the brain and the computers and AI systems.
Amnon, you think it's cyborgs or AI by itself? The next.
I'm a true believer on kind of a man-machine cooperation. Doesn't have to be implants, but a man-machine cooperation. That means technology is at some point, it's not there to replace people, is to make our work much more efficient, much more interesting. And this is really the real promise of advanced technology.
Nice to hear from both of you your views. These are views, of course, many people have opinions, but I think your opinions weigh a lot more than anybody else's probably today. Going forward and building on the last question, given where we are today, we said about big data and memorization and overfitting being more or less where we are today, without necessarily having clarity about whether there is a need for a next scientific revolution. It seems there is a need for a next revolution, but we're not sure. Are we hitting a wall? Do you think we're hitting a wall in terms of what large language models can do today? And if so, how do we overcome this wall? Are we hitting, first of all?
Yeah, I'm not sure we're hitting a wall, but I would say that we are reaching kind of the law of diminishing returns in terms of the architecture of the language model, in terms of making it bigger and multiple experts. And I think there we will be reaching diminishing returns. The big promise, I think, is how to properly work with data. I'll give you an example. One of the key features of these architecture, the transformer architectures, is a sequence-to-sequence learning. It's called autoregressive or next token prediction, but what Tommy mentioned, this pre-training phase. Now, sequence-to-sequence learning is something that we had in the past. It was called RNN, recursive neural networks. But RNN didn't work so well. And transformers is a much, much better version of sequence-to-sequence learning. It doesn't compress the context like RNN did. There is a price to pay, computational price to pay for it, but the performance is way, way better than what we had. Now, sequence-to-sequence allows you to do machine learning, which is not just, give me X and Y, give me the problem X and the solution Y, and I need to figure out what is the function such that f of X is equal to Y. That's classical machine learning. Sequence-to-sequence allows you to do also intermediate supervision. It's also called the chain of thoughts. So there are a number of examples, empirical examples. For example, let's assume that I take a language model and I give it many, many millions, trillions of examples of a number multiplication, say up to 4-digit multiplications, two numbers, x1 and x2, up to 4 digits each number, and I'm giving you the answer. So input, output, and train a large language model to try to learn how to multiply numbers. So it turns out that the language model, since it's basically overfitting, would not learn how to multiply numbers. It will kind of interpolate. So if you give it now 5-digit numbers, it will not be able to multiply because it didn't figure out how to do multiplication, the algorithm behind multiplication. But if now, since we're talking about sequence-to-sequence, you don't just give it x1 and x2, the two numbers, you also give it the steps of multiplying the two numbers, just as a string, just the steps of multiplying the two numbers, and then the result. And you give it many such examples. This is what's called chain of thoughts or intermediate supervision. Then the system really learns how to multiply two numbers. So this intermediate supervision is a key to make this jump from overfitting massive overfitting into something which can maybe discover rules. And now the question is how to create this intermediate supervision at scale. This is an open problem, right? Because now if we had a super intelligence that can generate for us the intermediate steps, kind of the single hop in a multi-hop reasoning at scale, then we can train the existing architecture of language models are good enough to train on this data and imitate that super intelligence. But we don't have the super intelligence. But how to create this data at scale is the open problem, but it's a data problem. It's not an architecture problem.
So what do you think?
Yeah.
What do you think as we are running towards the end? Is it a data problem? Are we hitting some other wall? Should we try something different beyond data and chain of thought? Tommy, sorry.
Oh, well, yeah, I agree. If you could have all the steps a Turing machine does, and we have the data reflecting those steps, you then can learn whatever program the Turing machine is running, even if it's very complicated. But I'm not sure that's only a data problem. Humans developed intelligence. How did they do it? Certainly not using big data or special data. So I think if we are hitting a wall, there is diminishing returns. Seems if you look at how much Gemini or Claude 3 is better or relative to GPT-4 and so on, you see there are very small differences. If we are hitting a wall, we may look at how human intelligence works. Or maybe a different approach would be, let's try to simulate the evolution of human intelligence and see whether we learn something about it.
Tommy, thank you very much. Just briefly for the audience, we'll come back with Tommy on event number 7 in June or July, I don't remember, where we'll talk about a book Tommy you recently wrote, and we'll have a long discussion about this, go more in depth. Amnon and Tommy, it has been really a pleasure to be with you. I'm stopping a minute early because I want to just inform the audience for the next event. So Pascal or Sandra, we can share the screen and come back to Tommy for a goodbye. The next event on the series will be on the Global AI Leader Series of INSEAD will be with Cedric O, who's a co-founding advisor of Mistral. So we'll see a European view. We'll talk about Europe and innovation and regulation. Cedric was also a minister of digital in France and a board member in Artifact. We'll come to this next and continue the discussion on the tour around the world. Before that, we can remove the slide. Tommy and Amnon, any last comment in the last minute, just very briefly? Are you optimistic going forward? And any big wisdom word if you have? Amnon, what do you think?
Optimistic, and it's very good to have people and ex-students like you both to be involved. One reason I'm optimistic for the future.
That makes us very responsible, Amnon. How do you feel?
I'm very optimistic, and having an advisor like Tommy was really life-changing, really life-changing.
Same for me, Tommy. It's been really a pleasure and an honor, as I said. Very nice, and looking forward to seeing you in person also. Thank you very much.
Thank you.
Thank you.
Bye-bye.
Bye.